So today we're going to have our third lecture on spectral graph theory. Actually, there'll be one more lecture kind of related to spectral graph theory when we talk about expander graphs. In fact, there's a connection between spectral graph theory and de-randomization. So two topics that we'll have seen before. In today's lecture, I want to talk a little bit more about, finally we'll get to really talk about eigenvalues and eigenvectors, hence the name spectral graph theory. And I'll make some connections to this sparseness cut problem we talked about last time, and conductance, and then we'll talk about this question about how fast do random walks on the graph G get to the invariant distribution. So I'll recap once again some of the setup we have. So we're always going to be sort of in the back of our minds having a fixed undirected graph G that we're studying. And there's a very special probability distribution on the vertices of G, namely the invariant distribution or stationary distribution, which we denote by pi. It's proportional to the pi of u is proportional to the degree of u. And this is the uniform distribution and the notable special case where G is a regular graph. And it's also the distribution where if you have a random walk in a graph and it's tending to any distribution on vertices at all, then it's this invariant distribution. And for almost all graphs, except for some annoying cases when the graph is disconnected or bipartite, you have the property that if you start at any vertex and walk for a really long time, then the distribution on vertices will tend eventually to this stationary distribution. We also have this linear algebra setup. So we think about, we're always thinking about functions, mapping vertices to real numbers, which we can also identify with vectors of height n, if there are n vertices. And we have the special inner product for two functions, which is kind of like the correlation between the two functions f and g, or the average value of f of u times f of g, f of u and g of u, but taken with u being drawn from the stationary distribution. Our favorite setting actually for functions, the ones we truly care about, are functions that have range 0 or 1, or indicator functions of subsets of vertices. And for example, if f is the indicator of a subset of vertices S, then if we look at the inner product of f with itself, which on one hand we sometimes, following geometry conventions, denote as the squared norm of f. On the other hand, if we plug in the definition, we see it's the expected value of f squared under this distribution pi. F's values are 0 and 1, so the square is just the same as the unsquared version. So this turns into the probability that a random vertex drawn from the stationary distribution pi is in the set S. So in the most normal case of a regular graph, when pi is the uniform distribution, this is just a fraction of vertices that are in S. Or generally, it's proportional to the number of edges touching the vertices in S. And it's sometimes called the volume of S. And in the previous lecture, motivated by this thing that we're going to study today, the random walk on the graph, we introduced this operator, a transition operator. You can also think of it as a matrix. So it transforms one function to another function. And if you apply k to a function f, it gives you a new function, kf, where the value of kf at a vertex u is like the average of f's values in u's neighborhood. So it's kind of like a little diffusion operator. And we checked that it had some nice property. If the graph is a regular graph, then k is nothing more than the adjacency matrix scaled by 1 over d, the degree. And in that case, k is a symmetric matrix. In general, it's not a symmetric matrix, but it does have this property that's greatly enjoyable. It's related to symmetry, called self-adjointness, which says that the inner product of f and kg is the same as the inner product of k, f, and g. And in either case, you can easily check that they're both given by this more interpretable quantity. It's the expected value of f of u times g of v when uv is a random edge. So you can sort of think of this as also sort of the meaning of the k operator. As I said, we were motivated to introduce the k operator because of thinking about random walk on graphs. And remember, when you're thinking of this random walk on graph, you should, when you actually do it, you're like tracking the location as time goes on of a particular vertex. You're hopping from vertex to vertex. But in a more abstract sense, what you should really do is keep track of the probability distribution on where the vertex in the random walk will be as time goes on. So even if you start at a deterministic location, then even after step 1, you have a probability distribution on where you'll be in time 1 and a probability distribution on where you'll be in time 2 and so forth. And we really want to keep track of these probability distributions. The invariant distribution has the special property that if you start your random walk at a vertex drawn from the invariant distribution, then at each subsequent time step, the location of your random walk will also be in the invariant distribution. But it's more usual to start your random walk from, let's say, like a deterministic fixed vertex, or some worst case distribution rho on vertices. But as we saw before, it connects to this transition matrix K. If you say, OK, what I'm going to do is I'm going to start my random walks from a vertex drawn from this arbitrary probability distribution rho, and then I do t steps of the standard random walk. At each step I go to a random neighbor of where I am. Then the distribution of where I am at time t is given by rho, thought of as a rho vector, times the tth power of the K matrix. Finally, with K in hand, we introduce this one more matrix L. It's sort of like a trivial twist on K. It's just K subtracted from the identity matrix. But the real reason we introduced it, the normalized Laplacian matrix or operator, is because it has this property. When you do the inner product of f with LF, you get this key quantity that we love so much, the quadratic form of f, so the local variance of the function f across edges. OK, so the last thing we did was we proved a theorem that told us that the matrix L is a very enjoyable matrix from a linear algebra point of view. There's these like freakish, annoying matrices in linear algebra that have bad things like they don't have an orthonormal basis of eigenvectors. That's gross, but L doesn't have this property. L does have an orthonormal basis of eigenvectors. And another beautiful property, in general, eigenvalues of a matrix can be complex numbers, even if the matrix has real entries. But this L has real eigenvalues, which is also very pleasant. And our theorem was this. This Laplacian matrix L has an orthonormal basis of eigenvectors. So there's some basis for all n-dimensional vectors, phi 0, phi 1, up to phi n minus 1. And phi 0 is a particularly simple vector. It's the vector of all ones. And it has, they have associated eigenvalues, lambda 0, lambda 1, up to lambda m minus 1. Things are ordered by the magnitude of these eigenvalues. And we verified that this lowest eigenvalue corresponding to the all ones vector is 0. So this is even another nice property. All the eigenvalues of L are non-negative. And we saw before the largest eigenvalue is at most 2. And it's equals 2 if the graph is bipartite. Just to remind you from linear algebra, what does it mean, eigenvalue? It means it's a function or a vector where when you multiply it by L, you just get a parallel copy of the vector. You get a scaled version of phi I, scaled by the eigenvector lambda. So I will tell you what is the merit of getting into all this eigenvalue and eigenvector stuff in just one moment. But I want to make one more remark. Once we have this, we can say something very concrete about the eigenvectors and eigenvalues of K. Does anybody know what one can say about that? Does anybody know what the eigenvectors for K are? Yeah, they're the same. They're also phi 0 through phi n minus 1. And the ith eigenvector is 1 minus the ith eigenvalue of lambda. So this just comes from the fact that K is trivially defined in terms of L and vice versa. So this is K is identity minus L. And well, let's just verify what's going on here. You see, since K is I minus L, we see that, well, if you happen to consider what happens if I hit phi I with K, well, it's I minus L phi I. And this is going to be easy. This is this is I phi I, which is just phi I, minus L phi I. And phi I is an eigenvector for L. Its eigenvalue is lambda I phi I. So we get 1 minus lambda I phi I. So we're like, oh, great, ta-da. K also has phi I also has the property that if you multiply it by K, you just get a scaled copy of phi I. That proves that phi I is an eigenvector, and its eigenvalue is 1 minus lambda I. So K also has a great, it's equally delicious matrix. It has the orthonormal basis of eigenvectors, the same phi's. And its eigenvalues are just 1 minus all these things. So they're between -1 and 1, which is also kind of pleasant. I mean, so that's very nice. And I'll write, so therefore, K has the same eigenvectors. And I might also say eigenfunctions because we're identifying functions and vectors in this world. And its eigenvalues, which I'll call kappa I, are 1 minus lambda I. Okay, and we have the ordering that like -1 is less than or equal to kappa n minus 1 is less than or equal to kappa 1, less than or equal to kappa 0, which is always 1. Yep.
Are we going to talk about like is it the case when you apply k like a lot of times with any like starting distribution, it ends up in like the stationary distribution?
Yeah, this is the idea that we'll get to towards the end of the lecture, that we're going to want to show that unless you have like some weirdo situation like a bipartite graph or a disconnected graph, if you start at any vertex in your graph and do a standard random walk, the distribution of where you are quickly gets to the stationary distribution. And you can see from this first bullet point that's very much related to like what happens if you start with a vector and you multiply it by a high power of k. And maybe you can already see, I'll get into this soon. I mean, this is the reason why it's so great to have these eigenvectors and eigenvalues for L and for K, because as I'll mention shortly, what does it mean that you have a basis? It means that if you have any function at all, such as rho, you can express it as a linear combination of these phis. And then if you're interested, like, hey, what happens when I multiply this rho by K? It's very easy if you know the expression of your vector in terms of these phis, because multiplication by K effectively just replaces phi I by kappa I times phi I. So if you do this over and over again, you'll easily see how these coefficients in this linear combination change. And that will help us understand how quickly this rho kt turns into pi, or something very close to pi. So in fact, let's introduce some notation for this. This is not standard notation, but I like it. So given any vector or function, okay, so it's living in this n-dimensional vector space, so and we have an orthonormal basis, we can uniquely express it as a linear combination of the phis. So the notation we need is just notation for the coefficients. So we'll just write this. Okay, so we're going to write f as like something times phi 0 plus something times phi 1, where these are real scalars. And I like to write f hat 0 and f hat 1 up to f hat n minus 1. Okay, so these f hat i's are scalars. One reason, as I mentioned last class, if you just tell this entire story, but for the fixed graph G, which is the hypercube graph, then you exactly recover analysis of Boolean functions, and this f hat notation will make sense. Although you'll choose to index your phis not by the numbers 0 through 2 to the n minus 1, but by these subsets of coordinates 1 through n. Great, so that's just some notation. Once we know that every f can be expressed as a linear combination of the phis, just giving names to the coefficients. So let's do that thing that I was exactly talking about. Let's take this equation, I'll call it star. And let's ask ourselves the question, suppose I had some f and somehow I figured out these coefficients, the f hat i's. Great. And now I was interested in doing the same thing for LF. I kind of wanted to understand what is the expansion of LF or KF. I mean, it's basically the same kinds of calculations. Well, if we multiply this, did I call it star? star by L on both sides, a vector equation there, multiplied on both sides by this matrix L, well, we get the sort of expansion for LF. So you see, OK, so we can, everything is linear, so we'll get, this is a scalar, f hat 0, and we'll get L times phi 0 here. But by definition, L times phi 0 is lambda 0 times phi 0. We happen to know that's 0, actually, but let's not necessarily remember that just yet. And similarly, I think will happen for all the other, f hat I, phi I terms. So what we'll get is that this is lambda 0 times f hat 0 times phi 0 plus lambda 1 times f hat 1 times phi 1 plus dot 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 plus lambda n minus 1 f hat n minus 1 times this. So once we, on one hand, moving to this is like a little bit unnerving. You had some nice, vector f, and now I'm making you think of it in this different basis. But once you get over that psychological hump, you're very happy because now, if I'm interested in applying L or K or something to my function, I can immediately and easily deduce what its expansion is in terms of these basis vectors. Okay. As I mentioned, we also have this property that lambda 0 is 0. So this term drops out if we want. OK, so you could say, if you want to write this in some funny symbols, we could deduce that L f hat I is lambda I times f hat I. Another nice thing is this. Let's say we also had, I should also mention, now if you imagine applying L to this again, well, this will go up to lambda I squared. And if you apply L t times, you'll just multiply all these coefficients by lambda I to the t. So that's going to play a role when we start studying random walks. Let me also note another formula, though. Say we have another function g, and we're like, OK, I'll write it as a linear combination of these phi's. Well, one thing we're always interested in when we have two functions, f and g, is their inner product. And let's see what happens. Imagine we take this inner product of f and g, and we plug in f's expansion, and we plug in g's expansion. So we have the inner product of two sums of n things. It's linear, so you can expand, the inner product is linear, so you can expand it all out, and you'll get sum over I and j of f hat I g hat j times the inner product of phi I and phi j. But now a good thing happens, right? The phi's are orthonormal, which means precisely that this is 1 if I equals j, and it's 0 if I does not equal j. So all the summands where I differs from j drop out. And when I equals j, this just becomes 1. So we get this nice formula. The inner product between f and g is sort of like the dot product of their coefficients in this basis. And this is really like, the dot product formula for inner products in the standard inner product world. And it's also like this Plancherel or Parseval formula we saw in the special case of analysis of Boolean functions. OK, so it's another way if you manage to know your functions, f and g, in this basis, and you have an easy formula to figure out their inner product. So let me write some corollaries of this fact that we will use sometime. I'll put them on this board so we can save them. And in fact, we kind of saw all these corollaries again in the analysis of Boolean functions lecture, but specialized to the hypercube case. So here's some corollaries. One, if you look at f squared length, i.e. f's inner product with itself, then we get that this is the sum over all the i's of the squares of these coefficients. Another nice corollary is, one thing that we're sometimes just interested in is the expected value of f, or the average value of a function f. Well, this is, by definition, the inner product of f with the constantly 1 function. And the constantly 1 function is also, phi 0. So really, this is already written sort of in its own expansion. We have a coefficient of 1 on this guy and a coefficient of 0 on all the other phi's. So by this formula, this is just f hat 0. OK, so when you write f in this form, one nice thing that happens, this is really the constantly 1 function, by the way. And this is also nice. This is the expected value of f. OK, so this is a constant function that's just constantly equal to f's mean. So this first piece of the expansion is like the mean of f, and like these are kind of the fluctuations of f from its mean. As a corollary of this, sort of hence, we get that the variance of f of u is, well, the variance is the expected square, that's this, minus the square of the expectation, which is the square of this. So we're just taking all these terms and taking away the f hat 0 squared term. So this is the sum over all I strictly bigger than 0, in other words, not equal to 0, of f hat I squared. And finally, the last nice formula, which is going to be good to compare to this one, this quadratic form that we care about. OK, we remember that's the inner product of f and LF. Well, here's f, here's LF, and now we just need to multiply their coefficients together pointwise and sum them up. So this, we can see it's the sum over all the i's. You can omit the 0th one if you like, of lambda I times f hat I squared. Okay. So I know it's like a lot of formulas, but they're going to have some payoff just now. In particular, we're going to get some payoff by comparing these two quantities.